Okay, so what if I told you that faster-than-light phenomena could actually exist without breaking the fundamental rules of physics? Yeah, I know, it sounds like straight-up science fiction, but a brand new framework is suggesting it just might be possible. We're going to dive into how black holes could be the key to completely rethinking what we know about speed, about information, and really the laws of the entire universe.
So you probably heard the classic story, right? The campfire story of how black holes glow, Hawking radiation. This idea that pairs of virtual particles just pop into existence near the event horizon. One gets sucked in, and its partner zips away as radiation. It's a really powerful image, and it's catchy for sure. But as our source points out, it's also pretty misleading. It gives us a what, but it kind of skips over the how.
Okay, so if that campfire story isn't the real deal, then what is? I mean, how does a chunk of space-time that's famous for trapping even light itself end up glowing at all? Well, the answer might not be some random quantum quirk, but something that looks a lot more like a beautifully logical, totally law-abiding cosmic machine.
Now, this new framework has a bit of a mouthful of a name, Casimir Coupled Tachyonic Venting, or CCTV for short. And I know that word tachyonic probably sets off alarm bells, right? Faster than light travel? But hold on. Here, it's referring to patterns that just appear to move super fast, not actual particles breaking any speed limits. So forget about particles popping out of thin air. Instead, I want you to picture this as a machine, with real, understandable parts working together to turn raw gravity into light.
And this machine, it's actually pretty straightforward. It runs on this neat three-step loop. First, you've got a pump right there at the edge of the black hole. Second, you've got a filter sitting in the space just outside of it. And third, and this is absolutely crucial for physicists, there's a system of balanced books that makes sure every bit of energy is perfectly accounted for. No magic, just physics. All right, so let's pop the hood on this thing and take a look at the two components doing all the heavy lifting. First up is the pump, which is what generates all the energy. And then we have the filter, which gets to decide what that energy actually turns into.
So the engine of this thing, the pump, runs on this really cool process called temporal amplification. See, right near a black hole's event horizon, the gravity is so intense, it creates this weird region where quantum fields don't travel faster. They grow. They swell in place, gaining energy without actually moving through space. You know, the perfect way to think about this is microphone feedback. You get that high-pitched squeal, not because the sound is suddenly breaking the sound barrier, but because the exact same sound wave is being looped and amplified over and over until it gets incredibly loud. That's temporal amplification. It's a gain stage, not some kind of cosmic catapult. Okay, so once the pump cranks up the energy on these quantum ripples, they run into the filter. And this filter has two different modes. The static Casimir effect, well, it acts kind of like the frets on a guitar. It decides which notes or which frequencies of light are allowed to ring out and escape. Then there's the dynamical Casimir effect, which is even cooler. If the boundary of this filter region is moving, it's like pushing a swing, the motion itself does work and literally creates real particles of light.
So we've got this really elegant cosmic machine, right? A pump and a filter. Simple enough. But here's where it gets really interesting. The real payoff is that this model doesn't just explain how black holes glow, it also gives us a fresh way to tackle two of the biggest, most frustrating headaches in all of modern physics. So, headache number one. This is the big one we all learned in school. Nothing, and I mean nothing, can travel faster than light. It's the universe's ultimate speed limit. Now, this theory doesn't suggest breaking that rule, not at all, but it does reframe it in a really fascinating way. Right, so the key to understanding this is this little phrase, FTL in the channel, causal in spacetime. So, what on earth does that mean? Well, it means that inside the very specific quantum lane or channel created by the black hole, a pattern can look like it's moving faster than the light around it, but it's really an illusion of perspective. No actual information, no signal you could control ever breaks that universal speed limit. It's kind of like watching the crest of a wave zip across a lake. The pattern is fast, but no single drop of water is actually keeping up with it. All right, on to headache number two, the famous, or maybe infamous, information paradox. See, the laws of quantum mechanics are very clear that information can never, ever be destroyed. But what happens when something falls into a black hole? Where does all of its information go? It looks like it just vanishes, and that breaks a very fundamental rule. Well, this theory suggests the information isn't gone, it's just recorded differently. Think about it like a stereo music track. If you only measure the total volume, all you're going to hear is hiss and noise. The music, the actual information, is hidden in the subtle timing and the relationships between the left and right channels. This theory says the same thing is happening with black holes. The information escaping isn't in the volume of the radiation, but in these hidden correlations, the phases between the light waves. It's all still there. You just need the right kind of stereo to hear it.
So, what's the big takeaway here? What does all this mean? Well, this isn't just some clever thought experiment or a cool idea on a whiteboard. The CCT framework makes very specific, very testable predictions about what we should be seeing when we look closely at the universe.
So how could we actually prove any of this? Well, the theory predicts specific observable fingerprints we could look for out in space. We should be able to find these subtle, regular timing patterns in the radiation, what they call phase ripples. We might also see these evenly spaced spikes in the energy that look just like the teeth of a comb, created by that Casimir filter. It even predicts a species ladder, where lighter particles would get vented out before heavier ones. These are all real, concrete signatures that astronomers can actually go out and search for.
But honestly, this goes way beyond just black holes. The author actually sees this whole framework as the lens for a much larger project called infinite data. The goal is to learn from nature. If a black hole can encode information into the subtle structure of quantum states to survive the most extreme environment imaginable, maybe we can engineer technology that does the same thing, creating incredibly robust new ways to communicate.
And really, that leaves us with this incredible final thought. Black holes might not be these cosmic destroyers of information at all, but instead the ultimate demonstrators of lawful, structured data transmission. I mean, think about it. If nature itself has figured out how to send a coherent message out of an object that traps light itself, what does that tell us about our own future? It suggests there's a whole new language written into the fabric of the universe, and we might just be starting to figure out how to read it.